Welcome to Two Projects. In this video, we are going to explain about the project that is TFEGRU, Time Frequency Enhanced Gated Recurrent Unit with Attention for Cloud Workload Prediction. So before getting into the execution, first let us understand what is this project about. Cloud computing. It has become extremely important in today's technologies landscape because it allows users and businesses to access computing power, storage, and network resources whenever they need them without having to own or maintain a physical hardware. These resources are provided through centralized data centers that manage and distribute the services efficiently. So this setup it makes it possible for companies to focus on their applications like storing data, running analytics on large data sets, that is big data, or hosting web apps and mobile applications without worrying about the underlying infrastructure. Cloud providers also ensure that these services comply with the service level agreements that are SLAs, which are agreements that guarantee a certain level of performance and availability. So, in this context, accurately predicting workloads, that is, estimating how much computing or storage resources will be needed at a given time, is extremely important. If a cloud provider underestimates the workload, it can lead to slow performance or even downtime, which might violate SLAs and frustrate users. On the other hand, overestimating workloads means allocating more resources than necessary, which wastes computing power and increases costs. By predicting workloads correctly, providers can strike a balance, ensuring that resources are used efficiently, costs are minimized, and users get reliable performance. This makes workload prediction a key part of managing cloud systems effectively. So, predicting this workloads in cloud computing is not easy because the way resources are used can change rapidly and unpredictably. The usage patterns called workload traces are often irregular and can spike suddenly and vary across different time periods. This makes it hard to find stable patterns that can be reliably predicted, and additionally, cloud systems generate massive amount of data across many servers, which often contains irrelevant or repeated information. This noise makes it even more difficult to make accurate predictions. So, traditional methods like simple regression can't handle the complex non-linear relationships in the data, and even standard machine learning models only improve predictions slightly. More advanced methods like deep learning, including recurrent neural networks that are RNNs, they face challenges too, such as remembering long-term trends and managing high-dimensional data. Because of these difficulties, it is clear that more sophisticated workload prediction techniques are needed to help cloud providers allocate resources efficiently and maintain high service quality. So, to overcome with all such issues, this project proposes a new model called Time Frequency Enhanced GRU with Attention Unit. So, that is TFEGRU to improve cloud workload prediction. Unlike traditional methods, this model is designed to capture both the short term fluctuations and long term trends in workload data. It combines GRU layers with the intense normalization, channel embedding, and attention mechanisms, allowing it to focus on the most important parts of the data while filtering out irrelevant information. And to further improve the accuracy, the model uses a channel independent approach that reduces noise and keeps the temporal relationships intact. At the same time, the embedding layer adds channel specific information, helping the model understand the unique characteristics of the different data streams. So, this combination ensures that TFE-GRU model learns more effectively and provides more reliable predictions for cloud resource management. And here, to improve the prediction accuracy even further, the system employs that is incorporates time frequency enhanced block, that is TFEB. This block extracts important features from both the time and frequency aspects of the workload data, allowing the model to capture complex patterns that may not be visible in just one domain. By combining this with a GRU network, the system effectively models sequential dependencies, understanding how current workloads relate to past patterns. So, this attention mechanism that It will help the model focus on the most relevant historical data. It improves long term forecasting also. Finally, the output layer generates the predicted workloads, which are evaluated using metrics such as mean squared error and mean absolute error. So, this design ensures more accurate predictions, allowing cloud providers to allocate resources efficiently, reduce waste, maintain compliance with service level agreements. Moving on, to further improve the performance of the workload prediction, the system uses extension models, two hybrid models. So, the first one is combining bidirectional GRU with TFEGRU and an attention mechanism. So, by processing sequences in both forward and backward directions, it captures richer temporal dependencies and extracts more relevant features from the data. This results in reduced prediction errors compared to the base TFEGRU model. And the second model is combination of GRU, TFEGRU with the attention and LSTM. This combination leverages the strength of each algorithm, enhancing temporal modeling, robust time frequency feature extraction, and focused attention on key historical patterns. As a result, this model achieves the lowest mean squared error and mean absolute error among all the models, delivering superior predictive performance and more reliable cloud workload forecasting. Moving on to the implementation. To implement this project, here we have followed the steps which are mentioned in the flow of work. So let's understand how we have implemented. First step. The first step is setting up the project environment. So this involves creating a Flask application to the server that is service the web interface, initializing SQLite database for storing user information, and creating the necessary directories to store models, datasets, and upload files. So this ensures project has structured environment to operate smoothly. And then we load and pre-process the data. Next, the dataset is loaded and prepared for modeling. Missing values are handled and features are scaled using normalization to ensure the models learn effectively. The dataset is then split into training and testing sets and reshaped into a format suitable for time series models, allowing the sequential dependencies of cloud workload data to be captured. Then comes model setup. So here at this stage, four models are defined and trained or loaded if they are already available. So here GRU, which is a base model capturing sequential patterns. And then TFE GRU model that combines GRU with attention and time frequency enhancements for better short and long term pattern recognition. Then the extension one that is B1 TFEGRU, which adds bidirectional processing to TFEGRU, capturing sequences in both directions for richer temporal insights. Then extension 2, that is by TFEGRU LSTM. It combines bidirectional GRU, TFEGRU, attention, and LSTM layers for the most robust feature extraction and temporal modeling. After that, once the models are ready, predictions are made on the test dataset. Evaluation metrics like mean squared error, mean absolute error are calculated to measure accuracy. Visualizations are generated to compare true workloads against predicted workloads, helping to assess model performance at a glance. And next comes user authentication, where the system allows users registration and login. New users can register with their details stored in the SQLite database. During login, credentials are validated to ensure secure access, enabling only authorized users to perform predictions or view model results. Then comes data interaction. So users can interact with the dataset through the web interface. The system displays dataset statistics such as total number of records, features, and training, testing split. It also shows sample records, helping users to understand the structure and the content of the data before making the predictions. Then comes the prediction part, where users can upload a CSV file with new data for workload prediction. So the uploaded data is pre-processed similarly to the training data, then fed into the selected model. The system generates a summary of predictions, including average, maximum, and minimum workloads, along with a detailed table showing each record's input features and predicted workload. Then comes model performance displays. So finally, the system presents a comparison of all the models. Metric tables show MSE and MAE for each model, while plots visualize true versus predicted workloads. So this gives users a clear understanding of which model performance best, that is, which model performs best, and the effectiveness of the proposed enhancements. So this is how we have implemented the project. So to implement this project, basically we need hardware and software requirements. In hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. And software requirements are application of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is all about the overview of the project. Now let's execute. To execute, let's open the code folder that contains source code files. These are the source code files in the code folder of the project. Let's understand each of them. So this is the dataset folder in which we have dataset that we will be using in the front end. And this is the model folder in which we have algorithm information that will be loaded into the project code during runtime of the application. And this is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. Here we have templates folder. So this folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And then here we have app.py file. So this .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And this is one Python file that is important for this project. And this is Windows batch file, run app. So instead of executing this project through command line interface, we have created this Windows batch file. And this is the database file. So to execute this project, we need to double click on this Windows batch file. So double click on it, click on run. So here if you observe, app file has been compiled. And now this command, it will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port, unless configured differently. So just wait for a while. So this is the address where application has been hosted. Copy it and paste it in any web browser. So now open Chrome because I prefer that, and I've copied already the link. Paste the link here, click on enter. This is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So first we need to get registered. So click on new registration here. So you need to fill in all these details for creating an account. I have already registered, so I'll directly log in. So click on user login here. Give your username and the password. And now click on login. So we are redirected to the other page of the project. We are redirected to admin dashboard. So here, first we need to click on load and process Alibaba dataset to perform, that is to check the cloud computation time. So click on load and process Alibaba dataset. So here total we have 10,000 records, and here we have 9 features in the dataset, and we have 8,000 for training the models and 2,000 data for testing the models. And here we have multiple features. So let's understand them based on which only the cloud resources will be allocated. So here, machine ID, the first value we have is the machine ID, which is a unique identifier for each machine or the server in the cloud environment. It helps to track workloads and resource usage for the individual machines. Then we have timestamp. This records the specific time at which the resource usage was measured. It is essential for analyzing trends over time and predicting future workloads. And here we have CPU util percentage. So it indicates the percentage of CPU usage by the machine at a given time. High values means CPU is heavily utilized while lower values indicate idle capacity. And then here we have memutil percentage. That is, this represents the percentage of memory being used by the machine. It helps to understand how much RAM is occupied versus free, which is important for workload planning. Then we have MEM-GPS. It is typically refers to the amount of memory that is RAM available or consumed, usually in gigabytes. It complements MEM-util percentage by providing absolute memory usage. And here we have MKPI. This stands for Machine Key Performance Indicator, and it is derived metric summarizing overall machine performance. It combines CPU, memory, network, and disk usage into a single performance code. Then we have netin. So this is the incoming network traffic to the machine, usually measured in bytes or packets per second. It shows how much data the machine is receiving over the network. Then we have net out. This is the outgoing network traffic from machine. It reflects the volume of data being sent from machine to other nodes or clients. Then we have disk IO percentage. This shows the percentage of disk IO, that is output IO usage, representing how busy the storage system is. High values may indicate potential bottlenecks in reading and writing the data. So this is all about the data. So these are the sample first 100 records, and these are the parameters used for predicting how much cloud computing resources will be allocated. Now let's click on train TFEGRU algorithms. So click on that to train the models. So just wait for a while. Models are being trained on this data set of 8,000 records. So here models have been trained, and here we have the algorithm performances also. So the first model is the existing GRU model, and here we have mean squared error, that is 0.08, and here we have mean absolute error. Accordingly, we have for proposed model extension by TFEGRU and the extension 2, that is by TFEGRU LSTM. Here if you observe, this extension 2 model, it has the lowest error than any other models in this project. So here if you observe, this model, it has the lowest error rate. And let's see through visualization. So here we have model performance. So this is the existing GRU. Here on x-axis we have test cloud data, and on y-axis we have working rate prediction. Red color represents, so this red color represents true workload, and this green color represents predicted workload. Here, if you observe, there is so much of gap with the red and green color line. They are not merging. So with this, we can understand that the application is not accurately predicting. And this is TFE-GRU. Here on x-axis, we have test cloud data, and on y-axis, work rate prediction. Similarly, we have red color as true workload and green is predicted workload. If you observe, it is better than GRU, but here also we have slight variations. So let's move on to the extension. And here this is the extension one. Here also red color is true workload and green color is the predicted workload. If you observe, there are very less gaps than the first two models that we have developed. With this, we can understand that this has the less error rate than these both. So it means actually it works well with the prediction of cloud computing resources. And here we have the other model, extension 2. On x-axis, we have test cloud data, and on y-axis, we have workload prediction. And here we have true workload, green is representing predicted workload. And here also, if you observe, almost green color is merging with the red color, which means application is accurately predicting the workload. So this is all about it. Now let's do the prediction. Click on predict cloud workload, and let's upload files here. So click on choose file to upload it. And here it is asking only to upload in the CSV format. So we are supposed to upload only in the CSV format. So click on choose file, select the test data to predict the cloud computing resources. Click on open, and now click on predict workload. So this is the data set that we will be uploading now. Click on predict workload. So this given information, it will be pre-processed to match with the trained model, that is trained data set. And then it will be fed to the trained model, then trained model will be giving us a prediction. So just wait for a while. So here we got the prediction. So total records that we have given are 14 records. So that is why we have total 14 predictions. And the average workload predicted is 28.7 percentage, and maximum workload is 54.4 percentage. And minimum workload is 5.90. And here we have input records. So this is the record number 1 and this is the input features that we have given, and here it is predicted as 31.45. Accordingly, here we have second record and second input features, predicted workload. And here we have third record, third input features, third workload. Accordingly, for all the 14 inputs that we have given, it has predicted the workload of the cloud computing. So this is how you need to do. Now click on log out. In this way, by using the TFEGRU with the extension that is by GRU and LSTM, the application will be able to correctly and accurately predict the cloud workload. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.